Hello everyone. Today we are going to discuss a new chapter, that is coordination chemistry, or simply say complex chemistry of complexes. Now, before starting with this coordination chemistry or the coordination compounds or the complex species, let's begin with some basic terminologies or the basic terms that we will often used in coordination chemistry. So let's start with the basic terms. So chapter is coordination chemistry. Some basic terms. First of all, let's take up simple salt. What is the meaning of simple salt? We all know that when an acid reacts with base, neutralization reaction takes place and a simple salt along with water, unionized water, is formed. So simply saying, simple salt contains single cation and single anion. So we have looked at this acid plus base neutralization reaction, and this gives you salt plus unionized water. So let's take up this. We have this HCl plus sodium hydroxide, when this gives you sodium chloride plus HCl. So this sodium chloride, which contains one basic radical and one acidic radical, that is simple cation and simple anion, that is what we call as simple salt. Take this H2SO4 plus AOH, when this gives you A2SO4 plus H2O. So you look at this, potassium sulfate contains simple cation and simple anion. So these types of salt which contains simple cation and simple anion is known as simple salt. Then we have mixed salt. Now, in case of simple salt, we have a simple cation and simple anion. The salt containing simple cation and simple anion, that is known as simple salt. But if the salt contains more than one cation, then we have a term which is used known as mixed salt. Example, look at this: sodium potassium sulfate. So we have sulfate 2 minus sign, sodium plus potassium plus. So this is a salt in which we condense two types of cations, sodium and the potassium. So these type of salts which contains more than one cation or more than one types of ion, this is one we call as mixed salt. Third, we have molecular or addition salt. Molecular or addition salt. So let's discuss what is this molecular or addition salt. Now, when two or more aqueous solutions of salts is allowed to vaporize. So we have suppose salt 1, we have salt 2. Now we have two different types of salt. Now, these two different types of salts are mixed together and they are allowed to evaporate when the crystals are obtained. That crystals that we obtain when two or more than two different types of salts taken in stoichiometric ratio are allowed to evaporate when the crystals are obtained. That crystals are known as molecular or addition salt. So these molecular or addition salts are crystalline compounds which are obtained when two or more than two different types of salts taken in stoichiometric ratio are allowed to evaporate. That is what we call as molecular or addition salt. So definition says when two or more aqueous solution of salts taken in stoichiometric ratio are allowed to evaporate crystals of molecular or addition salt are given off. So this is molecular or addition salt. So basically in this case we are taking two or more than two different types of salt in that stoichiometric ratio and they are mixed together and they are allowed to evaporate when certain crystals are obtained, and that crystal is what we call as molecular or addition salt. Now these molecular or addition salt is of two types. So let's discuss. Molecular or addition salt is of two types. We have double salt and coordination or complex salt or species. So these are two types of molecular or addition salt. Now let's differentiate and I will give you examples also. So first of all, coming to this double salt. So let me define this double salt. So these double salts are those salts, types of substance which retains its properties only in crystalline state. So these type of salts retains its identity only in its crystalline solid. Once this salt crystalline compound is dissolved in water, it loses its identity. So those type of salts which retains its identity only in crystalline state and not in aqueous solution, those are known as double salt. So definition is salts which retains its identity only in crystalline solid state. It loses its identity in solution. In solution. So let's take this example. Potassium chloride, we have this aqueous solution. plus magnesium chloride aqueous solution plus 6 water molecules. When this is allowed to evaporate, we get this compound potassium chloride, magnesium chloride, 6 water molecule, which is known as carnallite. It is an ore of potassium or magnesium, from which we can extract potassium or magnesium. So this is the substance. Look at this, we have 1 mole of potassium chloride, 1 mole of magnesium chloride, and 6 moles of water, and is allowed to evaporate when we get the crystals of this carnallite, that is salt. Similarly, take this potassium sulfate, aluminium sulfate with 24 water molecules. This gives you potassium sulfate, aluminium sulfate, 24 water molecules, which is known as potash alum. It is ferrous sulfate, ammonium sulfate, 6 water molecule gives you ferrous sulfate, ammonium sulfate, 6H2O, which is known as Morse salt. So, when preparing this molecular addition compound known as double salt, we take some stoichiometry ratio of 2 or more in 2 different types of salt, and they are allowed to evaporate when unnecessary water molecules or other substances are removed when we get the presence of this double salt. So, definition says these types of salts retains its identity only in solid state. Once they are dissolved in aqueous solution, they loses their identity. So look at this. Let me give you this in the same example. So we have aqueous solution of potassium chloride. So this contains potassium and Cl minus N. So before formation of this double salt, this aqueous solution will give you the taste of positive taste of potassium and positive taste of chloride ion. Magnesium chloride contains magnesium ion plus chloride ion. So the aqueous solution before preparation will also give you magnesium chloride, magnesium ion taste as well as chloride ion taste. We have this solid. Now this solid, when dissolved in water, again this gives you A plus ion, Cl minus ion, Ag plus ion. So once this salt is dissolved in water, it immediately changes into ions. This salt is completely soluble in water when this gives you the ions. So the aqueous solution of this salt will also give you the taste of chloride ion, potassium ion, magnesium ion. So this salt exists in solid. Once this is dissolved in water, this converts into free cations and free anions, and this will give you all the taste of individual cations and anions present. So look at this. Before formation of this salt, solution gives the taste of potassium ion, magnesium ion, chloride ion, and when this salt is also dissolved in water, again this gives you taste of potassium ion, chloride ion, and the magnesium ion. That means individual components of double salt does not lose its identity. This was the individual component, this is also individual component. So this is what we call as double salt. Look at this second case, potassium sulfate. We have potassium ion and we have sulfate ion. So solution will give you taste of potassium ion and sulfate ion. Aluminum sulfate, we have aluminum ion and sulfate ion. So this will give you case of aluminum and sulfate. When this is again dissolved in water, this gives you potassium ion, sulfate ion, aluminum ion. Again, the aqueous solution gives you case of potassium, sulfate as well as aluminum ion. So individual components again showing here retention of identity. Take this ferrous sulfate, we have ferrous ion, we have sulfate ion, ammonium sulfate, we have ammonium ion plus sulfate ion. When this is again dissolved in water, this more salt dissolved in water, this gives you ferrous ion, sulfate ion, ammonium ion. So again, the aqueous solution of this more salt gives you the taste of ferrous, ammonium as well as sulfate ion. So these types of salt which exist only in solid state, which retains its property or individuality or the identity only in solid state, and it loses its identity or existence in solution. So this is what we call as double salt and the example. So that means in double salt, each and every individual ions will show the positive phase. So we have shown this here. Then the second category is correlation compound. Now double salt says retains its identity only in crystalline state. Whereas in case of coordination compounds or the complex compound or the coordination of complex species, that species which retains its identity in both aqueous solution as well as the crystalline state. So those types of salt or molecular addition compounds which retains its identity both in crystalline state and the aqueous solution, those are known as coordination compounds. So coming to coordination compound, definition: retains its identity both in crystalline state and in aqueous solution. So it retains its identity both in aqueous solution as well as crystalline state. So those type of compounds are known as coordination compounds or complex species. So example of this. So we have to look at this. Suppose we have KCl aqueous solution with FeCN2 aqueous ferrous cyanide. Now this is allowed to evaporate when we get this. K4FeCN6. So before this, solution contains K plus ion, Cn minus, ferrous cyanide. This contains ferrous ion and cyanide ion. So before formation of this species known as coordination species or the complex species, the aqueous solution gives the taste of potassium ion, cyanide ion as well as ferrous ion. Now we have this compound K4FeCN6. When this K4FeCN6 is dissolved in water, this gives you A plus and this complex anion. This is what we call as complex anion. Now, the aqueous solution of this coordination species gives the taste of potassium ion only. This does not give the taste of ferrous ion, does not give the taste of cyanide ion. Entirely a new species is formed which is known as complex species. Now this complex species does not have free iron plus 2 and free cyanide ion. So these complex aqueous solution of this complex species does not give the taste of ferrous iron as well as Cl minus iron. That means the aqueous solution of this complex species loses the identity of the individual ions. Before this, we have potassium ion, cyanide ion, ferrous ion. But after formation of this complex species, the species aqueous solution does not give the taste of ferrous ion or cyanide ion, but it gives the taste of this complex species FeCl6 4 minus. So this is what we call as coordination compound. Let me give you one more example. Look at this. Potassium sulfate aqueous solution plus ammonia aqueous solution. Now when this is allowed to evaporate, we get this. Now this aqueous solution contains copper ion and sulfate. So this will give you taste of copper and sulfate. So aqueous solution gives you the taste of copper ion and sulfate ion. Once this is allowed to evaporate, this gives you this species, but this species when dissolved in water gives you this complex species. So this does not give you the taste of copper ion because copper ion combines with ammonia to give you a complex species, but this gives the taste of the complex species. So individual ions loses its identity. So the complex and the aqueous solution. The identity of this complex species retains both in crystalline state as well as aqueous solution. So this is what we call as coordination species. And so we are going to focus more on this coordination species. So basic difference is coordination compounds retains its identity both in aqueous solution and in crystalline state, and individual ions loses their identity. Some of the ions may give their taste, but most of the ions will not give taste. Whereas in case of double salt, this retains its individuality only in crystalline state. Once this is dissolved in water, it loses its individual identity, whereas the ions will retain their individuality. So this is two types of molecular addition or molecular salt. Now coming to this coordination species, let's define coordination species or complex species. So to begin with, coordination species, coordination compound, coordination complex or complex species or coordination species is a species which is always written in square bracket and which contains a central metal atom or ion to which some other ions are attached to. So we have a species which is always written in square bracket, and inside this square bracket we have a metal atom or metal ion to which certain other atoms are attached. So that particular species is known as complex species or coordination species. That coordination species may be cationic form, may be anionic form. So we have looked at this species which contains a metal atom or ion through which certain other ions or molecules are attached and which is written in square bracket. So in any species which is written in square bracket is known as coordination species, and coordination species must contain a central metal atom or ion and some other species which is attached to the central metal atom or ion. That is what we call as coordination species. So we have looked at this. We'll just give you example. FeCN6. So these species which is written in square bracket, this is written in square bracket. The species which is written inside this square bracket, that is known as coordination species, complex species of coordination entity. And inside this coordination entity, we must have metal ion, and this is the other atoms or ions or molecules which are attached to the central atom. This is what we call as ligand. So we must have a central metal atom or metal ion to which some ligands are attached. And all these must be enclosed in square bracket. This is written in square bracket. So we have looked at this. Again, we have this metal ion. But this is ligand. In here, the ligand is negatively charged ligand, but here ligand is neutral. That is molecular form. So whatever may be the case, a complex species is always written in square bracket, and this contains a metal ion and ligand. So ligands are firmly bonded to the metal ion or the metal atom, and this is written in square bracket. So these coordination species may contain a simple cation or a complex anion. This may also contain simple anion or complex cation, or this may also contain a complex cation as well as complex anion. So if you look at this, this is clear for the two. So we have simple cation, complex anion. Take this, we have complex cation, simple anion, or we can also have a look at this. We have complex cation and complex anion. So means these coordination species or coordination entity or the coordination compounds may contain simple cation, complex anion, simple anion, complex cation, or this may contain complex cation as well as complex anion. So basically, coordination or complex compound or species always written in square bracket, and the contents of square bracket is we have a central metal atom or metal in some other oxidation state to which some other species known as ligands are firmly bonded. So these type of species is what we call as coordination of complex species. Then we have a term which is known as ligand. Now we have to define this term ligand because already while defining this coordination space we can use the term. We have a central metal atom or ion and we have ligands. Ligands are firmly bonded to central metal atom or ion. So let's define what is ligand. Now these ligands are those species which donates a pair of electrons to the central metal atom or metal ion, and these are bonded to the central metal or the metal ion through coordinate or dative bond. So since the bond between metal ion or the metal and the ligand is a dative or coordination bond, so these are known as coordination compounds. So ligands are those species, either this is negatively charged, this may be neutral molecule, or this may be a positively charged species, which is attached to the central metal and through dative bonds. So when we are saying dative bonds, this is always giving you a pair of electrons to the central metal atom or ion. So these are species. So this may be cationic, this may be anionic, or this may be neutral molecule, which donates a pair of electrons to the central metal atom or ion, forming a dative or coordinate bond. So these ligands may be a neutral molecule, this may be an anionic species, or this may be a cationic species. But the basic purpose of this ligand is these ligands donate a pair of electrons to the central atom. Now since this is donating a pair of electrons to the central atom accepts a pair of electrons. So electron donor is Lewis base. The electron acceptor is Lewis acid. So ligands are Lewis base and the metal ion or metal atom is Lewis acid. And the bond formed between these metal and ligand is additive bond. So we have looked at this. So we have metal and this is ligand. This is metal, this is ligand. Now ligand donates a pair of electrons to the central atom. So this pair of electrons is coming from ligand to metal, and this is forming a dative bond. This is dative bond. So these ligand may donate a pair of electrons, may donate two pairs of electrons. So at least one electron pair donor. So this ligand is electron pair donor. So electron pair donor. So this is Lewis base. Now metal is accepting electron pair. So this is electron pair acceptor. So electron pair acceptor is Lewis SC. So we can classify this ligand as a substance which donates a pair of electrons to the central metal and forms a dative bond with the metal. In some other case, some of the ligands may also show donor as well as acceptor property, but in most of the case, in majority of the case, ligand acts as a donor partner, and what is metal acts as an acceptor partner. But there are some cases or some ligands which shows both donor as well as acceptor property, like carbon monoxide, cyanide, and NO plus. These ligands shows donor or acceptor property. So In complex species containing these types of ligands, ligand will act as a donor partner as well as acceptor partner, and the metal will also show acceptor as well as donor partner. So in both the case, this will say ligand will act as an acid as well as base. Similarly, metal will also act as a base as well as acid. But the general characteristics of ligand is ligand has to donate a pair of electrons to the central atom and it acts as a donor partner, that is Lewis base. And the metal has to accept a pair of electrons from the ligand forming a dative bond. So metal will act as an electron pair acceptor on Lewis acid. So this is what we call as ligand. Now since ligand is bonded to central metal, so the number of ligand atoms bonded to central atom gives rise to the coordination number. So let's define what is coordination number. Cn. So this coordination number is the number of ligand atoms that are bonded to the central atom or the central metal ion through dative bond, or the number of chemical bonds formed between the ligand and the central metal atom or ion, that is known as coordination number. So definition is number of atoms of ligand bonded to central metal atom or ion through dative bond. So actual how many atoms of ligand is bonded to the central atom, or we can also say number of chemical bonds formed between ligand and central metal atom or ion. That is also defined as coordination number. Now to define this, we have a formula. Coordination number is equals to summation of number of ligands into density. We may have a ligand, but this ligand may contain more than one ligating site, then density may be more than one. If any given ligand contains only one atom, that given ligand bonded to the central atom only through one atom, then we say the density is 1. The same ligand, if suppose some other ligand may contain two atoms that can simultaneously bonded to the central metal, though ligand is 1, but the number of atoms bonded to ligand is 2, so we say density is 2. Or there may be some ligands which contains 3 ligating sites, and these 3 atoms may simultaneously form bond with the central atom. So the ligand is 1, but density is 3. So coordination number is number of ligands into density summation of this factor. Example, take this FeCN6 4 minus. So look at this. This central metal is bonded to 6 cyanide ion. So therefore, coordination number of Fe is 6. 6 ligand, density is 1. Copper is bonded to 3 ammonia molecule. for ammonia molecule, ammonia density is 1, so coordination number is 4. Aluminium hydride, aluminum is bonded to 4 hydride and density is 1, so coordination number is 4. Take this. This complex species, we have two different types of ligand, ammonia and Cl. Cl is a monodentate, ammonia is also monodentate. So we have coordination number 4 plus 4 into 1 plus 2 into 1. So this is coordination number 6. So take this En 3. So En, this is ethylene diamine that we'll discuss in different types of ligand. So ethylene diamine is a bidentate ligand, density is 2. So number of ligand is 3, and each ligand is then having 2 densities, so that we have this 6. Oxalate ion, number of ligand is 3, density is 2, so coordination number is 3 into 2, 6. So simply saying, coordination number is how many ligand atoms are directly bonded to the central atom through that bond, or how many chemical bonds are formed between the ligand and the central atom. That defines the name is called as coordination number. So this is the formula that we often use for finding coordination number. That is number of ligands and multiplied by its density, summation of total number of ligands and its density. That is what we call as the coordination number. So next is effective atomic number rule. That is EAN, effective atomic number rule. Now look at this. While discussing chemical bonding in 11, you say the basic purpose of formation of chemical bond is to gain stability, and the first point that we take up while defining stability is ability to attain noble gas configuration. So any particular species which can have noble gas configuration will lead to the stabilization. So during chemical bond formation, either by sharing of electron, we get noble gas configuration, either by losing of electron or by gaining of electron, we get noble gas configuration. So in the same way, to explain the stability of the coordination species or the complex species, and similar to this noble gas configuration, effective atomic number rule is proposed. That means we have a complex. This complex contains central metal, atom or ion, and plus some other ligands are bonded to this central metal. So when ligand is bonded to central metal, ligand is transferring at least a pair of electrons to the central atom. So after gaining this electron pair from the ligands, what is the actual number of electrons present in the central atom? So the total number of electrons present in the central metal, including the electrons coming from ligand, if this gives you the noble gas electronic configuration, then that leads to the stabilization of the complex. There may be variation, but this says the total number of electrons, including that coming from ligand, should be having noble gas. That is what we call as effective number of effective atomic number or effective number of electrons. So this En, just from example point of view, atomic number of metal minus the oxidation state of metal in the complex plus 2 times number of ligands. Because each ligand atom will donate a pair of electrons. So this actual number of electrons, that is including those electrons coming from this ligand, that is what is called as effective atomic number. To force stabilization, most of the case this has to follow atomic number of the next noble gas. Let's take this example. FeCO5. This is complex. Iron is zero oxidation state. So therefore, effective atomic number of iron. Atomic number of iron is 26. Oxidation state is 0, so minus 0 plus 5. We have total number of ligands is 5 and each ligand is going to take a pair of electrons, so we say this 2. So this comes out 26 plus 10, 36. This is atomic number of noble gas. FeCN6 4 minus. Effective atomic number. Cyanide is minus, so total negative charge is minus 6, but each species carries minus 2, so total positive charge should be plus 2. So effective atomic number is 26, oxidation state is 2, so minus 2 plus 2 into 6. Density is 1. So therefore, look at this comes out to be 26 minus 2, 24, 24 plus 12. So this is effective atomic number. Yeah. 36. 24 plus 12, 36. That is FeCN6 P minus. This is total negative charge is 6, so total positive charge will be plus 3. Effective atomic number 26 minus oxidation state is 3 plus electrons coming from ligand is 2 into 6. So this comes out to be 34. So there is a violation of this EM rule. So simply saying, this is how you calculate the effective atomic number. So to define this effective atomic number, you should know the atomic number of the metal, oxidation state, and the number of ligand atom that is bonded to central metal. Take this. C2O4 P minus. So cobalt is bonded to 3 oxalate ion. Charges is 3. So each oxalate ion is having minus 2. The total negative charge is 6. The total positive charge should be plus 3. So the total charge comes out to be minus 3. So effective atomic number of cobalt. Cobalt is 27 minus oxidation state is 3. Now look at this. This is bidentate ligand. Density is 2. So how many ligand atoms are there? 6. And each ligand atom will donate a pair of electrons to 6 into 2 into 6. So again, number of ligand is 3, but density is 2. So total 6 ligand atoms are bonded to cobalt. So each ligand atom will donate a pair of electron, that is 2. So 27 minus 3, 24 plus 12, 36. So this is how we define it. So in many of the cases, this rule may be violated. But majority of the case what we find is when this ligand forms bonds with central metal, the effective number of atoms present in the metal comes out to be mostly the next normal gas atomic number, that is effective atomic number, simply calculation of effective atomic number. Then we have this classification of ligands. Classification of ligands. How ligands are classified? We have defined ligand, we have defined density of the ligand, again we will come to the density while defining this types of ligands. First, based on density. Density means number of ligating atoms in a ligand. How many ligating atoms are present in a given ligand, that is known as density of the ligand. So based on this density, ligands are classified as monodentate. That means number of ligating atoms present in the ligand is 1, density is 1. Example, Cl minus, Br minus, I minus, that is H2O, NH3. So this is some examples of monodentate in which density is 1. Then we have bidentate. Density is 2. Example, check this. This is ethylene diamine. Ethylene diamine, simply written as EN, ethylene diamine. Now look at this. This nitrogen is having a lone pair of electrons. So this nitrogen acts as a ligating site. This also acts as a ligating site. So look at this. We have one ligand, but there are two atoms through which bond can be formed simultaneously to the central metal. So ligating site is 2. So we said it is density. This is 1 10, second that. So density is 2 here. Take this C double bond O, O minus, C double bond O, O minus, that is C2O4, 2 minus, oxalate ion. So these oxalate ion, look at this, we have this oxygen with extra electrons. So this is denting side, this is also denting side. Take this carbonate ion, carbonate. So this is denting side, this is also denting side. So take this CH3, CHNH2, CH2, NH2. 1,2-diaminopropane, we have denting site, then density is 2. Take this CH2, 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 NH2, 1,3-diaminopropane. Again, look at this nitrogen, denting is, denticity is 2. So, if the ligand contains more than 1, or simply if the ligand contains 2 atoms through which chemical bond can be formed with the central atom, then we say this density is 2. So, similarly, we can have if the density is 3, then we have this. Example, look at this. Tridentate, density is equals to 3. Take this CH2, CH2, NH, CH2, CH2, NH2, diethylene triamine. You have 2 ethylene group with 3 NH2 group. Diethylene triamine. Now look at this. Each nitrogen is having a pair of electrons. So we have one ligand, there are 3 atoms through which bond can be formed with the central atom. So we said this is known as tridentate. Then we have, if the density is more than 3, then we can simply say that it is polydentate. Polydentate ligand. And the best example is EDTA4 minus. It is ethylene diamine tetra acetate ion. E for ethylene, D for diamine, T for tetra, A for acetate ion. So look at this. So we have ethylene, 2 carbon, diamine, 2 nitrogen, acetate, 4 acetate groups. So if you look at this, now nitrogen having lone pair, this is acting as the denting site, nitrogen lone pair, denting site. Oxygen lone pair, oxygen, electron pair, oxygen, electron pair, oxygen, electron pair. So this ethylene diamine contains one ligand, but there are 6 atoms through which chemical bond can be formed with the central matter. So since the ligating side is 3, so we say this is hexadentate. So this comes under polydentate. So based on denticity, we define these ligands as mono, bi, tri, tetra, penta, hexa, etc. depending on the number of ligating sites present. So this is first classification. Now let's go to second. These ligands may contain charges or may not contain charge. So based on charge, these ligands are classified as anionic ligand, cationic ligand, or neutral ligand. Anionic means negative charge, example Cl minus, Br minus, I minus, CO3 2 minus, C2O4 2 minus, SO4 2 minus, H minus, NO3 minus, etc. These are negatively charged ligands. Or we may have a neutral ligands, neutral molecules, like we have looked at this H2O, oxygen is acting as a ligating site. We have NH3, ammonia acting as a ligating site. We have RNH2 primary amine. We can have ethyl diamine, etc. These are neutral ligating, so neutral ligands. We can have cationic ligands in which the ligand carries a positive charge. In this example, NH2, NH3 positive. It is N2H5 positive. So these nitrogen having a lone pair, this is acting as a negative charge, but ligand contains a positive charge. So this is hydrazinium ion. Similarly, we can have NO plus nitrosodium ion. So these are based on the charge. These are defined as anionic ligand, neutral ligand, or cationic ligand. Then next classification is ambidentate. Ambidentate ligand. Now these ambidentate ligands contains two atoms which can act as a ligating site, but while forming the bond, only one atom is used at a time. So I repeat, these ligands contains two atoms which can act as a ligating site, but while forming chemical bond, only one atom is used at a time. So this is ambidentate. So contains two atoms which can act as ligating site, but only one atom is used at a time. So the best example is we have this Cn minus. That is, we have C triple N. So this is Cn, the negative charge. Nitrogen is also having lone pair electron. Carbon is also having a lone pair electron. So both these carbon as well as nitrogen can bond it through the central atom. So depending on, we can have this metal Cn, or we can have metal Nc. So these types of ligand is what they call as ambidentate ligand. Bonding can be through carbon or bonding can be through nitrogen. If the bonding is through carbon, we say this is cyanide. If bonding is through nitrogen, we say this is isocyanide. Similarly, we can have NO2 minus. So we have looked at this. Bonding can be through oxygen or bonding can be through nitrogen. So we have looked at this NO2 or MONO. Bonding is through oxygen, bonding is through nitrogen. M bonding to nitrogen, nitro. Bonding to oxygen, nitrito. So we can also look at this HCN minus thiocyanate. Bonding can be through oxygen, sorry, sulfur, or can be through same. So these types of ligands is what we call as ambidextrous ligand. Then next category of ligand is chelating ligand. So chelating ligand, coming to the definition of or the properties of chelating ligand, these are bidentate or polydentate ligand. Monodentate ligand cannot be chelating ligands. Either these are bidentate or polydentate. So these bidentate or polydentate ligands containing two ligating sites which can simultaneously bond with the central atom. If these are bonded simultaneously, these results in the formation of cyclic or ring structure. So those types of ligands are known as chelating ligands. So this is bidentate or polydentate ligands which forms cyclic or ring structure with metal atom or metal ion. So example look at this En, ethyl diamine. We can have oxalate ion, we can have carbonate ion, etc. So if you look at this, we have this metal. This metal forms bond with this. Okay, this is ethyl diamine. So bond is forming through both the nitrogen simultaneously. This results in the formation of cyclic or ring structure. So these types of ligand is what we call as chelating ligand. Now another category of ligand, that is some ligands apart from showing donor properties also show acceptor property. These ligands contains pi anti-bonding orbitals through which electrons can be accepted. Pi acceptor ligands. So these ligands contains anti-bonding pi orbitals vacant through which electrons can be accepted. Example, carbon monoxide, Cl minus, NO plus, we can have other also. So when these ligands forms bond with the metal, first ligand acts as a donor partner, and simultaneously these ligands also contains metal antibody pi orbitals unoccupied. So these can also accept electron density from metal. So this is donor, this is acceptor. So in both these cases, look at it, both ligand and metal is acting as a donor as well as acceptor partner. So these types of ligands are what we call as pi acceptor ligands. So these are certain categories of ligands that we often use in coordination chemistry. So this is the classification of ligands, different types of ligand that we use in coordination compound. So this is some basic terms concerning the coordination species.